Hello. Hello. Oh, wow. We've got more. Oh, wait. Am I either you're on mute or you're on mute? Okay. Hello. Hello. You've been. Hello, Sarah. Hello, All Smile. Hello, Miriam. Hello, Ashley. Wait. Oh.
What's wrong with you?
Hello, Steven's friends. Hi, Sarah. Hi. Also, oh, Gianna, that was like Gianna just like beamed in and out. Oh my God. Totally. All right, whatever. Um, uh, hi, Steven's perfect. Oh, that was, wait, was Steven in class? And wait, hi, wait. Okay, that's funny, I think. Good afternoon, Steven. All right, okay. So hello, Euban. Hi, Miriam. Oh, she said everyone. Is she the first person to do that this time? That used to happen. That's very nice to think of the other people. All right. Anyway, hi. Oh, wait, more people. Sorry. So hi, Sarah. Hi, hello, Ashley. Good afternoon, Montserrat. Good afternoon, Jada. Hi. That is so funny, Old Smile. I totally don't get it, but I know it's funny. Good afternoon, Gianna. Good afternoon, Stephen and Stephen's professor. Top of the afternoon, Abdel. Why does that crack me up every time? You'd think I'd be used to that by now. Okay. Afternoon, Jasmine. Hello, Brian. Good afternoon, Brianna. And like, we're going to just pretend that we didn't see Brianna for like a flash crazy moment. Not flash. I mean, a flash moment. Okay. Hello, Anthony. Whoa, Anthony's picture is something. Good afternoon. Yes. Wait, more people coming. Isn't it sad to think that like I literally could just do this for 75 minutes if I'm not careful? Like I literally, I'm not saying it'd be, but I could. Okay. Wait, so Sarah, Osmael, Ashley, Anthony. Oh, and hi, Jocelyn. Awesome. Oh, and then there's Abdel in the 3 dimension. There's Jose. 3 dimensions, yo. All right, all three of them. And he's pointing to someone. Okay, whatever. Who else did I not say? Yes, hi, Jocelyn. Hi, Sumaya. If I didn't say, I think I did. I'm not sure. Sorry. And I think I said hello to everyone. Oh, and hello, Katya. Okay. I think that's okay. So, okay. Yeah, I think that's everybody. Okay. I'm gonna, all right, so we're moving on. Okay, hold on. Oh, is that Osmail waving? Or is that hello? Yes, or is that like, wait, oh, and that's Abdel. Wait, that's so crazy. Are you guys like, wait, are you waving to each other? Are you like are you just, okay, that's so confused. Are you all like wait, I think I see what's going on. No, I totally don't. But are you all like in the floor of John Jay waving to each other from across the, are you just confused? You're just messing with my mind because you've now come to understand that it's an easy target. Oh, you are. Wait, you're in a class. What? Wait, what? Does somebody want to explain this? No, you don't. Like, this is weird. I feel like you are okay. You exist in 3D. I want to see some ID. I'll know that when I'll believe that when I see it. You're in the same cloud, okay, but you're like at different corners. Oh, that's so wild. Okay, I wish I were there. Do I? Oh. You would like to observe your fellow classmates in 3D. That's so okay. That's so funny. Okay, I'm getting distracted. Wait. Okay, that's so funny. All right. I wish I were there, which tells you what kind of life I had have. Wait, so you're all, okay, that's cool. And what's so sad too is like you're probably so, I could tell, but I mean you are. All right, I'm gonna shut up. Okay, that's very cool. It's also funny that you're saying observe your fellow classmates in 3D because in fact, okay, so like 3D or at least more than 1D is what's happening in physics class now, right? Like everything we had been doing in physics class was all about motion back and forth in 1D, in one line. And now just finally, as of lab 4 and problem 6 of homework 6, i.e. the big old duck, we finally segued into physics within higher dimensions of space. And we segued. The principle for understanding how to do physics in 2 dimensions or 3 dimensions, excuse me, or even higher, the principle is Galileo's principle of relativity, form number 4, and particularly form number 5, where we're saying, just to remind you, the big observation is that every 2-dimensional problem is really 2 one-dimensional problems occurring independently yet simultaneously. And approached that way, then we never need any new equations or new concepts to handle motion in a plane or motion in a cube, or motion within a solid 3-dimensional space. We just keep treating each axis as its own axis of space with equations applying to it in and of itself. And we assume that each axis of space is not affected or interfered with or interacted with but by any other dimension of space that's happening. But we assume that time is the interlinking variable between anything and everything that's happening among the different dimensions. That's the assumption we're making in the big old duck problem. That's the assumption that you make when you do lab 4. Now we have to move on from those results and start being even more precise and rigorous about how to deal with motion in higher dimensions and the way so we don't introduce any new equations. The whole point is we have all the equations we need for each one dimension at a time. We don't introduce new equations, but we start figuring out ways to break down one 2-dimensional situation into its constituent 1-dimensional parts. When things start getting elaborate and we start having things going off at angles and things like that, we have ways of breaking down motions into constituent 1-dimensional components. And the ways of doing that involve this thing called vectors. So now we want to start getting more involved with our understanding of and manipulation of vectors. That's the topic that's coming now, technically 2-dimensional kinematics. So that's the topic that we're going to really formally do with now, with one big homework assignment that that just got posted. You'll have a full week to do. I mean, next Wednesday, it's fairly big. You'll do what you can of it. Some of it will be old review and practice. Some of it will seem newer. But the topic that we're now involved in ever since labs 3 and 4, the topic that we're now involved in is vectors and motion in 2 dimensions. What's going to happen is, okay, on this page of notes, on this page of notes, pardon me, switch. I have a problem here. This is an example problem to demonstrate or to kick us off with the idea of adding displacement vectors in 2 dimensions. This problem is going to be very reminiscent of or similar to lab 3, which we never really talked about. Lab 3 was really your introduction to higher dimensions. And then I keep making references to lab 4 because you actually do something physical in lab 4. But lab 3, you might recall, you got a bunch of pieces of graph paper and you had to do this kind of strange activity on the graph paper, and you might have discovered, and so you were moving around arrows on this piece of graph paper in lab 3, correct me if I'm wrong, and you may have discovered certain things about how the arrows worked, or you might not have, and then at the end you might have had a theoretical problem that you solved about to test your knowledge gained from those arrows. Well, the problem that we're going to do today in a few minutes is reminiscent of that. it might be easier if you feel like you got a lot out of lab 3, or if you feel like you didn't get a lot out of lab 3, then this problem that we'll do today might retrospectively help you understand better, like why we did it in the first place. What we're going to do in a few minutes, so you might want to write this problem down. I'm going to explain it in a few minutes, and then we're going to actually hopefully break up. Well, yeah, we are going to break up into breakout rooms, or we're going to break out into break up rooms, or something. Breaking up is so hard to do. We're going to get into breakout rooms, and you're going to solve this one problem that's on the board here. I do have to ask you to copy it down first, because the board doesn't like travel into the breakout rooms so far as I know, or I don't know how to do that. So you're going to do this problem, and then you're going to come back and we're going to discuss the solution for it. It is not assumed that I've ever stood up and explicitly told you how to do this problem. Like every step in physics, it's assumed that by having taken all the prior steps in physics that we've taken, that this is a next natural extension of the knowledge and the information we already have. The idea is that every next step in physics is just that, is an extension of old ideas. It may be a push, it may be a challenging push forward from old ideas, but the idea is that every next step in physics should be figure outable from the prior ideas, and that's where the next step comes from in the first place. So don't think when you try to do this problem, don't think, wait, was there supposed to be reading on this, or was I supposed to have an instruction guide already on how to do this? No, like you're going to figure it out from some basic principles, or you're going to figure out how to figure it out. You're going to try it from basic principles that you already have at your disposal. And if you did well in lab 3, or if you remember it, or if you have notes from it, they might be very, very helpful to you here. So I'm going to read it out loud. I'm going to explain, and you're going to go into breakout rooms. Well, actually, yes. All right, let me do that right now. Let me just to make sure that you can read the handwriting and all of that. So it says, you walk 5 meters to the north, in a direction known as 30 degrees northeast. Okay. That's your initial displacement. You could say you walk from point A to point B. 5 meters is your distance, and your direction is 30 degrees northeast. Those two facts together make a displacement, right? Now, that's the first thing you do. That's just a fact. That would be in DFP, step 1. Now, before I go any, well, no, okay, I'll read the rest of the problem, and then I want to say some things about it. So you do that. You go 5 meters at 30 degrees northeast. Then from that destination that you arrived at, from your point B, you now walk 8 meters at 60 degrees southeast. And there's an arrow there underneath illustrating what you do there. And then the question is written to the side like this, sadly. The question is, from your initial position to your final position, what is your total displacement? Okay, that's going to be the question. Your question I'm asking you is to find total displacement from these two individual displacements that you undergo. Now, remember, displacement is an old concept in this class. It means distance and direction. So what I'm asking you for in the end is a total distance from point A to point C, and a direction that you ultimately went from point A to point C. But notice this too. This is now the old concept of displacement, but being applied to 2 dimensions of space rather than just being applied to a number line, like where we first saw it. So direction now is a little bit more of a specific idea and a little bit more of a detailed idea. When we ever have 1 dimension of space, 1 axis, 1 line, like in our very first homework assignment, direction is designated with positive and negative signs. You're either going that way or you're going the opposite way. You're either going positively or you're going negatively. It's still true. Now, for each 1 line, for each 1 axis of space that describes our motion, we still distinguish between the positive direction versus the negative direction along that line. But now, if we're in 2 dimensions, each dimension has its own positive and negative. So in fact, I should, to make this a little bit clearer, hold on. So if I'm, following Galileo and I'm establishing a coordinate system or something, I might say something like, I might draw a little compass or grid. And notice in this grid, I now say along the north-south axis, north is positive and south is negative, but independently yet simultaneously along the east-west axis, east is positive, west is negative. And within that grid, so if I ever want, so if someone says, what direction are you going now? I can't just say I'm going positively or I'm going negatively. Like that's ambiguous. That doesn't tell me enough. Do I mean positive like north or east or what? So what we do now is we open up, we from here on in, we call east, we call due east 0 degrees. And from here on in, we open up angles from the east. That's supposed to be a little theta. We open up angles from the east. And so from now on, to specify direction fully, we use some sort of positive acute angle and points of the compass in order to designate direction. So from now on, if I were to say 0 degrees, I mean due east. If I were to say 90 degrees, I would mean due north. If I mean something in between, right? If I were to just say literally just northeast, due northeast, what that would tacitly mean is 45 degrees above the eastern line. So if I say something like I did here in this problem, like 30 degrees northeast, what I mean is I'm heading some direction that's a little bit more eastern-ish than it is northern-ish, right? That's what 30 degrees means. In fact, literally, specifically, you may or may not have ever thought about this before, but if I say 30 degrees northeast, what I actually really mean then is 30 degrees north of east. That's what northeast means, especially with an angle before it. It means that much north of east. So I never, with this language, I mean, there's other ways you can describe direction, but this is a way, and this is a good physics way. So in this physics way of talking about directions in the plane, directions in 2 dimensions, in this way of thinking negative, I never need a negative angle. I never need an obtuse angle or anything like that. Everything is some acute angle, some angle between 0 and positive 90 degrees, and everything is in, and then has points of the compass. So if you're understanding what I'm saying so far, you might realize that if I say 30 degrees northeast, that's equivalent to saying 60 degrees east north, right? I could say that, and sometimes physicists do. Like, it's a little bit awkward. It's not the way like American people speak normally, but it's meaningful. If you follow, when I say northeast, I mean north of east. So I could sometimes talk about opening up an angle from the north, and then that would be east north. Generally, that's an awkward way to speak, but so this is the way I talk about directions now. So the first thing I want to say, so the problem that you're all going to solve. Oh, wait, hold on. I have to. Sorry, there's an interruption. I'm going to keep talking, but I have to move myself. Hold on. Hold on. I'm sorry. 1 second. Okay. I'll keep. I don't know if you can still hear me. Sorry. So okay. So you're gonna. So when I say, so I'm looking for total displacement here. In effect, I'm asking you to add 2 displacements together. I just disappeared, and get a total displacement. But please note that the total displacement that you have to get will have to involve a distance and a direction, and the kind of direction that it will involve must be an angle and points of the compass in the manner of what's given here. I'm still here. Sorry, this is all a little bit spazzy. Now, I'm not telling you how to do this. I'm saying it's figure outable. I'm not saying it's easy. I'm saying it's a simple question. I'm just literally asking you to add two displacements. It's simple for me to phrase the question, but that doesn't mean it's easy. It will take some work and some thought, and maybe looking back to lab 3 would help. I will tell you right now that the answer will, it won't be like 13 and it won't be like 90 degrees. Like you're not just going to add the numbers of those 2 arrows that I gave you. I would recommend first drawing a diagram, in fact, maybe even putting the 2 arrows tip to tail just to picture what's going on. But then you're going to have to do some work. Hold on, and I will give you hints and stuff like that. Sorry, there's a distract. Just bear with me for a second, or pardon me for a second. Hold on. Pardon me. So oh my God. Okay, sorry, this is the distraction. I'm sorry, just one second, just might as well see what so I'll be back in a sec. This was unexpected and not supposed to be part of class, but maybe you can see. I don't even know if you can see, but I'll be right there. Hold on, sorry. Okay. Okay. I had more to say, but okay, and I do have more to. Are you still guys? Wait, are you still there? I can't even see if you're still. Oh, cool. Okay, that's cool. Okay, that's the first time that's a new thing in class. Okay, and you might see her again in a second. Okay. So, okay, I'm going to give you a couple of hints about this. Oh my God, there's so much distraction. In a few moments, I am going to put you in breakout rooms to solve this. Let me give you a couple. Well, all right, let me ask you this before I go on. I do want to give you some hints and guidance, and then I'm going to put you in breakout rooms to try to solve this. I'm going to say right now, the closest thing you've ever done to anything like this may have been at the end of lab 3. Other than that, this is not a new exercise in an old instruction. Like, you will have to think through. And my biggest recommendation is to draw the first arrow, and then from the tip of the first arrow, start the tail of the second arrow and draw it, just so that you can picture. Yeah, draw the 2 arrows tip to tail, and then draw one big arrow going from the original tail to the final tip of the other one. And that big arrow that you draw that went from the original tail of the first to the final tip of the last, that's what you're looking for. Okay, like the big vector, the big arrow that completes this triangle, you're looking for that. That will be your total displacement, or put another way, The length of that arrow is the distance that you're looking for. And the exact angle that that arrow points at will be the direction that you're looking for. So I will say that if you draw these arrows perfect, and if you were to draw these arrows perfectly to scale, like, or really, if you were to draw them with a ruler and a protractor, then that final arrow you would get, if you were to measure it with a ruler and measure its angle with a protractor, well, that would be your answer. Like that, and that's true. Now, I'm not expecting you to do it that way. I'm not expecting you to draw it perfectly and measure your answer. And I don't want you to. What I'm saying, though, is that if you draw a rough sketch like that, they'll help you picture what you're looking for, like that final arrow that you draw. That does represent the answer that you're trying to get. So at least it'll be a good check. It'll give you perspective, like, if that arrow is longer than the other two, then you'll know your answer should be bigger than the numbers 5 and 8, for example. And if that arrow is pointing to the northeast, then you'll know your final answer should be some degrees to the northeast. So I would recommend that you do that. But that's not the way you're going to get the actual numbers to this answer. And this answer is exact numbers. Like your answer will be an exact length measured in meters and an exact angle, either to the northeast or the southeast or something like that. I will say that anything you might know from math class about right triangles certainly should and will be very helpful here. Like if you remember anything about right triangles, such as SOHCAHTOA or such as the Pythagorean theorem, that will be very helpful here. But let me also caution you, I'm not saying that if you put these two arrows together that you'll get a right triangle. Definitively not saying that. I'm saying that you'll have to think more than that, but I am saying that right triangles are very important because the x-axis of space and the y-axis of space are at a right angle to each other. And I'm saying my big hint here is that if you think about right triangles and arrows, you can use them to break up each of these two-dimensional motions into two independent but simultaneous one-dimensional motions, which is the big principle of all of this. So you're going to have to think, or I think you're going to have to think, but don't be discouraged when you're thinking like this is a fresh new situation. And I think that if you think enough, it'll make sense and you'll be able to do it. So that's what you're going to do in a second. There's a couple more quick things I have to say. One, and please write this down. Please write this down on another page of notes or something. Each one of these arrows is called a vector. Each one of these arrows that I've drawn on the page and the arrow that you're solving for, it's trying to find, a vector is an arrow that is used to represent a vector quantity, right? So we use arrows to represent quantities with magnitude and direction. The length of a vector represents the magnitude of the vector quantity, and the orientation of the arrow, i.e. the tip-tail orientation, where the tip is and where the tail is, the tip-tail orientation of an arrow represents the direction of a vector quantity. Okay, so from here, remember, vector quantities are quantities that have magnitude and direction. We're now dealing with magnitude and direction in higher dimensions of space. So we use arrows to represent these magnitudes and directions in higher dimensions of space. And it turns out by drawing these arrows somewhat to scale, by being at least careful about their length and their orientation, and by placing them at certain in certain chosen positions on the page, we can actually use these arrows to compute combinations of vector quantities. For example, if you place, and you might want to write this down, or please do write this down, if you place two arrows tip to tail, that represents the addition, the adding of vector quantities. when you want to add vector quantities, you place vector arrows tip to tail. And you'll see that when you work this out. Now when I split you into these rooms, again, let me just remind you, I'm asking you to do a little work and use a little thought or creativity to actually come up with numbers. You're actually going to get a final displacement for this situation, a certain number of meters that you will have walked and at a certain angle of direction. I think it's doable, it's sensible, it's work outable, but it's not obvious. The answer you get is not going to be 13 meters at 90 degrees or something. You are adding these arrows, but you're adding two-dimensional arrows. And the principle, the big hint or secret is that somehow SOHCAHTOA and right triangle math is going to come into play, because the addition of these two-dimensional quantities really can ultimately best be understood as two separate addition problems, each happening along one axis at a time, one axis independently, but at the same time, much like you found out in lab 3. If you really think back and realize in lab 3, that's what you were finding out, whether we use that language for it then or not. Okay, I'm going to, what time? Okay, so I want to, yeah, okay. I'm going to put you in breakout rooms, but before I do, can you just show me electronic hands if it's clear what you're about to try to do in your breakout room? Oh, that was fast. Thank you, Gianna. That's awesome. Thank you, Brian. Thank you, Tobias. Thank you, Anthony. Thank you, Miriam. That's awesome. So, great. Thank you, Stephen. Thank you, Katya. Thank you, Sarah. Thank you, Montserrat. Thank you, Brianna. Thank you, Jocelyn. Okay, so it's pretty clear okay, so you know what you're about to try to do. Okay, and again, and this is not a test. Yeah, this is not a test. This is not a test. This is just okay. All right, so I'm going to put you in the breakout rooms. I'm going to catch my breath for a second, but here we go. Oh, hold on one second. Okay, so when you get your assigned breakout room, please get, yeah, great. Okay, thank you. And I'll call you back in a few minutes. Great, thank you. Awesome. Okay. Hi, Kay. Sorry. So we're in breakout rooms working on a problem now that they wait, oh, and Abdel's back. Wait. So we're in breakout rooms. I just assigned you to one. They have the problem in the room. Well, it's on the screen right now. If you can see, you can copy that, but they have the problem in the room. If you they just started. We just went into the room. And who? Wait, Abdel is back. Abdel. Wait, Abdel. Abdel question. Are you good? Okay. Hello. Oh, okay. Hello. One second. Hello. Okay, great. Hello. I think that you're all okay. Great. Welcome back, everybody. Sorry about the distraction before. It's good to see you all back. Okay, I called you back because I want to have time to finish this before class is over. Can I just get a show? So we're going to go over this now, or I'm going to go. I would love to have a whole big discussion, but that might not be so efficient right now. Can I just get a show of hands? Did anybody think they, and I'm not asking you to share your answer unless you want to, but can I just know, raise your electronic hand or thumb if you think you got any kind of answer at all, like even if it's not right or wrong. Oh, okay, great. Oh, well, great. And even if it's wrong, like so in other words, you completed something. You actually got to the end of something. Oh, that's great. Wow. Oh, maybe, what, have you been sitting for oh, terrific. Okay. So maybe it was, okay, great. All right. That's actually very encouraging. Okay. Again, I feel a little bit bad. I mean, I would love to I would love to like hear things and trade around and share, but we only have 20 minutes. So I'm a little concerned that will be, well, yeah. So I'm just going to, forgive me, but yeah, I'm just going to go over it my way. But stop me definitely if you have any questions or you did it differently or you got a different answer or something like that. Okay. I mean, again, I feel really, really guilty. I'd like to actually hear but I just think then we'll never get, or anyway. This is how I do it. Okay. Here, I'm going to turn the page. Okay. The first thing right here the first thing in the top of the page is just my sketch that I was recommending before, where I put the two arrows, which from here on in are going to be known as vectors. I take those two vectors and I place them tip to tail, right? And that red vector that goes from the original tip of one to the final tail of the other, that represents my answer, right? So just to be clear, this sketch, this is not an answer or anything. This is a sketch that represents like. Okay, so that first sketch up there is a representation of adding vector quantities. Like, in other words, if this whole question is about how far and in what direction did you get at the end, we're really saying if you first walked this way and then you walked that way, if you add those walks together, what's your total walk that you've accumulated by the end, right? So in the case of displacement vectors, hopefully it makes somewhat sense that when we place the displacement vectors tip to tail, we are in effect adding them. And so what that red, the red arrow represents the answer we'll get when we add these vectors together. Now, again, if I drew that really precisely, I could even figure out the answer by getting out a ruler, measuring the length of that red arrow, and getting out a protractor and measuring the length of that red arrow, like below the axis. And that would be my answer. So one thing I am just arguing here or saying is vectors are not, when I say that vectors represent vector quantities, I don't mean that they're just like a loose analogy. I mean that they, I mean that they literally represent, in the way that graphs literally represent quantitative relations. If you draw vectors precisely enough, you can literally use your pictures to do math. Like, they are a computational tool. Okay. However, I don't draw that well, and maybe many of us don't. So there's got to be a way that I can use that that picture that's giving me a sense. I'm sorry, that picture also, that red arrow, that's telling me in advance that if I'm drawing these roughly correctly, I should expect that my final answer is going to be an arrow that's probably larger than 5 in length, but it looks like smaller than 8 in length. And it's going to be pointing in some kind of southeast direction if my diagram is at all to scale. So, that will give me a sense of what to expect for my final answer. But how do I get a final answer? Okay, with 15 minutes left, this is how. I'm going to take each one of those vectors, each one of those two-dimensional quantities, and I'm going to incorporate the idea that each one of those two-dimensional displacements is really two one-dimensional displacements occurring independently yet simultaneously. So I'm going to take each one of the individual vectors and zoom in on it and break each vector up into constituent X and Y components. Like, I'm going to zoom in. So I'm going to separately zoom in on this first vector, this first displacement. I'll turn the page. So I'll copy it on the next page. I'm going to say, I'm going to talk about that in a minute. Sorry. On this next page, I'm going to say, okay, this is my zoom in. If I'm going 5 meters at 30 degrees of northeast, what I'm going to say is, you know what, to go up at 5 meters at 30 degrees northeast is really to go some amount east while independently yet simultaneously going some amount north. Or in other words, if placing vectors tip to tail means adding them, then I'm going to say that even that original vector of 5 could be viewed, just like if I say what's 2 plus 3 and you say 5, and that's true, even the 3 itself is 2 plus 1, and the 2 is 1 plus 1. Like, every number that you add to another number is itself the sum of smaller numbers, right? So this 5 vector that's going off at an angle is actually the sum of 2 individual vectors, one that goes directly east and then one that goes directly north. If I go 5 at 30 degrees northeast, it's as though, and you know this if you live in Manhattan, if you live in New York City and you work in, or you go to school in Manhattan, right? You know that if you want to go northeast, you have to go some amount, you have to go some number of streets uptown, and then you go some number of avenues crosstown, right? And the sum of those 2 individual perpendicular motions gives you your overall displacement. So I'm going to break up the 5 into 2 constituent one-dimensional components. How am I going to do this? I'm going to use my knowledge of right triangles, right? So I'm saying that the 5 itself is its own individual right triangle. Notice I'm not I'm not saying, and this is a common misconception, I'm not saying that if we put together the 5 and the 8, we'll get a right triangle. We won't, actually. I'm saying that every vector in and of itself is automatically its own right triangle, because it's the sum of a y-axis piece and a x-axis piece. And if I want to get what those pieces are, I realize SOHCAHTOA applies. So I could say, for example, over here, this side is the opposite of 30, the vertical side, the y-axis side is the opposite of 30 degrees. So I could say something like sine of 30 degrees equals the opposite times over the hypotenuse. Therefore, that opposite side itself equals the hypothesis, the hypotenuse, right, in general, right? And so therefore, that side is 5 times sine of 30, right? Which in this case is 5 times 1/2. I mean, sine of 30 is 1/2. So it's like 2.5. And the other, and this is always going to work, right? You could on every vector you ever get, you can break it up into constituent parts using SOHCAHTOA. The other side, I use cosine because it's the adjacent side. I'm going to have to speed this up a little bit. Okay. So I do that to that one vector. Now that's over here in my mind. Now, separately, at the same time, the other vector, I could say the same thing. I could say that the other vector is 8 meters. It goes some amount east and some amount this time south. Now I can go a little quicker. Now I get the pattern. So this is 8 cosine, and this is 60 degrees. 8 cosine 60, and the side, that's because that's adjacent, and the opposite is 8 sine 60. And 8 cosine 60 means 4, and 8 sine 60 is 6.9 around. So now what does all this tell me? I want to do this a little bit quickly. We've got 10 minutes. What I'm saying is that when you go 5 meters to, what I'm saying is this. I'm going to make an XY chart here. What I'm saying is that at the end of the day, what we really did was we walked 4.3 meters to the east, and then we walked 4 meters to the east. And separately, independently, yet simultaneously, we first walked 2.4 meters to the north, and then we walked 6.9 meters to the south. So I put a negative sign there, like, because remember we said on the first page, like we're saying, like, this is our coordinate system. Pluses and minuses exist on each dimension simultaneously, yet independently. Right? So now I'm going to just go to the next page. We have 9 minutes, right? But the key point is this XY chart. The XY chart is dividing my world into an X-axis and a Y-axis that are each happening independently yet simultaneously. So if I broke up each of these vectors into 2 independent yet simultaneous components, it seems that first I walked 4.3 to the east, then I walked 4 to the east. At the same time, yet independently, I walked 2.5 to the north, then I walked 6.9 to the south. So I'm just going to recopy this on the next page. Sorry. So what does this mean? It means at the end of the day, what I did was walk 8.3 total to the east, and I walked a total of -4 0.4, right? I believe 2.5. How come I can't do that? That's ridiculous. But yeah, negative 4.4 to the south. So what does that mean? It means at the end of the day, if I'm looking for one big vector that represents my entire displacement, what I did in total was I went like this. I went 8.4 meters to the east. Why do I know to the east? Because it's a positive. And then from there, I equivalent went 4.4. I'm trying to draw this roughly to scale, 4.4 meters to the south, right? To the, so I tip to tail again, east and then south because of that negative sign. So at the end of the day, what I did, I can use Pythagorean theorem to get my total distance. My distance will be the square root of 8.3 squared plus 4.4 squared, right? Which approximately equals so 9.3. Right? And for theta, I'll put it over here, right? So at the end of the day, apparently I walked a total of 9.39 meters. And apparently I walked in a direction. Well, how can I get this? Well, I could do SOHCAHTOA, but backwards. I'll write like this. I know that the tangent, now I could use anything. I could use sine or cosine. I like to use tangent because I have the numbers, the opposite and the adjacent. Like, and maybe if I made a mistake using the Pythagorean theorem, maybe I don't trust my hypotenuse, but whatever, you could use whatever. But the tangent of theta, it should equal the opposite 4.4 over the adjacent 8.3. That's what the tangent should equal. Therefore, the theta itself should equal the inverse tangent, the arc tangent, right, of 4.4 over 8.3. And we have 6 more minutes. So on my calculator, I do 4.4 divided by 8.3. I get a number and I do second tangent or inverse tangent of that, whatever you want to say. And maybe I'm going a little bit fast right now. We can review this again, but I think, oh, sorry, I'm in radian. And for this kind of thing right now, I would recommend that you be in degree mode, which I totally am not in. Yeah, and so then you get approximately 27.9 degrees southeast. Now, okay, so first of all, I know we're very little time here left, but first of all, and I wish I could look at yours or see what, but you can see if you did it. I'm saying the answer to this whole thing is a vector that is approximately 9.39 meters long. So you walked, your total distance was about 9.39 meters. I say about just because I'm chopping off digits, but I mean, that is the answer, 9.3 meters. And the direction you walked was 27.9 degrees southeast. Now, your numbers may be slightly different because of rounding and digit. Like if you got like 28.9 or 26, but that's fine. But your number should be close to mine if they're right. And if they're wrong, no shame, because we've never done this before. But hopefully you can follow where I got these numbers. Notice, let's go back and check now. Notice that I got an answer that was pointing to the southeast and was a little bit long, was longer than 5 and actually a little bit longer than 8. So maybe my diagram was not drawn so well to scale. But the numbers that I got, like I didn't get 13 or something, or I didn't get 90 degrees. The total distance that I walked was not just the sum of 5 and 8 because I didn't walk in a straight line. I'm walking off at an angle, right? So the way to add two-dimensional displacements is to break each one up. Well, I should say in general, the way to add two-dimensional vectors is to break each vector up into 2 independent but simultaneous one-dimensional quantities add all them up, tally them all up in an XY chart, and then put them back together again with Pythagorean theorem. I did that a little bit fast, but I think that's the answer, and that is the procedure. That procedure is called adding vectors by components. Now, I'm going to stop. I mean, there might be questions, and I apologize if there are, and I'll hang out. I'll hang out after, the bell, this is over, for any questions or concerns or whatever. But let me say, with 3 minutes left, I want to say something important. We do have to have a midterm exam. Okay. Here's the deal. I'm going to say a lot more about it next class Monday, but I'm going to post some details in your Google Classroom. I've already placed some details. I'll place more. Please listen closely for a second. We're going to have a midterm exam. It's going to be it's a real thing, but I do everything I can to reduce the extraneous stress and just make it only as difficult as physics actually is. Okay. Here's the basic overview. And again, it'll be placed in Google Classroom and we'll be talking more about it. But here's how it's going to work. 2 weeks from tomorrow, two weeks from tomorrow, Thursday, November 10th, the midterm exam itself will be posted by 8 p.m. at night. It'll look like 3 big homework problems, essentially 3 or 4, like standard homework problems with lots of parts and all that. And you have to do full solutions, like 5-step method, whatever. But it'll be posted by like 8 p.m. Thursday night, November 10th. You will take it home, and under untimed, non-test conditions with no webcams or anything like that, you'll take the exam at home, take as long as you want on it, then you'll return it. You'll post it back through Google Classroom no later than 3:05 p.m. the following Monday. So it'll be posted Thursday night, November 10th. It'll be due back November 14th, right before class. In other words, an extended weekend to do it. 2 more points, and we'll talk more about it before we get there, but 2 more quick points about it, just so that a lot of points about it. But number 1, you'll get a practice exam in advance, like the week before. You'll get a draft of the actual exam. So you'll get a very, very good idea of what the exam would actually look like. And on that draft, you'll have time to practice and work it out on your own, and come to class and ask questions about the practice exam, like the last class or 2 before the actual exam. The way we review is I answer your questions about the practice draft exam. I will also post some solutions to the practice draft exam, not right at first, but in time for your actual thing. So you get to practice this whole exam before it's ever posted. That's number 1. Number 2, the actual exams, I hope you're listening right now, or hope you're hearing me. And this is not the last things I'll say. I just want you to know, since now it's starting to happen. It'll be posted November 10th. You'll have practice and time to prepare for it, for 2 weeks before then. But also, once it's posted, it is untimed, open universe. I'm going to talk to you more about what that means next week. But I just want you to know it is an open book exam, open notes, open text, open internet, open colleagues. Like, you are allowed to talk to colleagues while the exam is actually happening. We'll talk more. It's not because I'm an idiot. I'll explain more why I do that and all of that. But you will be allowed to talk to people while the exam's in session. A lot of things that you normally think of as cheating are allowed. Because and we'll talk more about that why, but I just want you to know that you'll have practiced before this. It will then be posted on a Thursday. You'll be allowed to help each other and all of that stuff. It's just that when you finally sit down to draft your final copy of your final solutions to this thing, and you turn it in on time, you cannot write anything down that you do not by that point understand in your own mind. Your job, and I know it's 4:20, I'll stop in a second, but your job on the exam is to be as thorough and detailed and show as many steps and as much explanation as humanly possible to convince me, to prove to me that you understand why the answers are the answers. Most of the answers you're going to know about before you even take that thing. And you'll know that I know that you know. You'll know the answers. That won't be the mystery. The mystery or the challenge is, can you prove to me that you understand why the answers are the answers? That's your job on the exam. So by the time you actually write it out, Your work will be your best personal, authentic understanding. And the more you explain, and the more you give diagrams, and the more you use different colors, and the more you have annotations, the more you show me that you actually get it, then the better you are. And if you write down things that you don't actually understand, even if they're accurate, then we're in the realm of cheating, and we'll talk about that. But anyway, I don't mean to just end on that note. But the bottom line is the exam will be posted November 10th, Thursday night. It'll be due back Monday, November 14th. There will be practice before then. And if anybody has real issues with that timing, if you have a real conflict, if you let me know, we'll work things out personally. But you have to let me know personally, and we'll work things out if there's like an issue or a conflict. But I think that works for most people. I think you don't have an orgo exam or something like that. But okay, so I know I'm over time now. I'm going to sit. I'm not going anywhere if you have questions or concerns, or if I just panicked you. But yeah, okay. If you get what I'm saying, then good. Thank you. Hope you enjoy the rest of your weekend too. Very much. Yeah. Thank you. Have a good. Awesome. Okay. Thank you. Have a great day. Yes. Thank you. Thank you. Thank you. Thank you.